Hello everyone and welcome back to my channel Intelligent Machines. I'm Dr. Mohan, PhD in Industrial Computer Science and Artificial Intelligence. Today in the series on diffusion model and image generation, we are going to look at something very interesting, which is inpainting using diffusion model. Inpainting means editing a specific region of an image while keeping the rest of the image the same. For example, we have the picture of Donald Trump here and we create a mask where the black area of the mask represent where we want to do the ink painting and the white area in the mask represent the part we want to keep as it is. And when we pass this kind of input to the model, we get something like this. The model generates a new image where the masked region is altered and the rest of the image remains coherent. Often this result looks very realistic. Now the question comes, where shall we use this in painting? You can use in painting to change the background of a product so that you can show your product in different backgrounds without having the hassle to change the location itself. You can replace object in a scene. You can do small edits like adding a glass to a face, or you can do outpainting by expanding the image beyond its original borders. This is another funny example where this is the original image of the cat and we replace cat with a dog, fox, lion, tiger, cat, and etc. Now the question comes, do we need to fine tune the diffusion model to do this in painting? And the answer is a little complicated. Nowadays, there are models who do fine tune for in painting tasks, but in this particular video, we are going to look at a new way, which is proposed by this paper called RePaint, where we do not need any training of the already present diffusion model we have. All the computation are going to be done during the inference time. So we do not need to fine tune the model to get good in painting results. So here is an example. So this there is a photo of a lady with a mask, and we want to inpaint in the masked region here. And you see we get different variation of the same image. None of these generated images are real. However, they look pretty realistic. Now I will try to explain the core idea of this repaint paper. So we start with an original image like this that you want to inpaint, and we create a binary mask which is shown by the color blue here, or this one, this mask. The zero in the zero in this mask represent the black part and one is the white part. So wherever there is zero, we want to inpaint those regions, and wherever there is one, we want to keep those regions. During the inference time, we start with absolute random noise. We run the denoising loop. So this denoising loop does two things. One, it passes the noise input to the model and gets the noise that needs to be removed, and using the scheduler it removes that noise. We'll see it in the code base just after this. And here we get a less noisy version of the noise we started with. So now we have a less noisy version, let's say at a timestamp t minus 1, x t minus 1. Then what we'll do, we take the reference image and we noise it to same extent, to the same timestamp, let's say up to t minus 1. So this one is doing forward diffusion step from reference image, and here we are doing backward diffusion step from random noise. And then we are combining both of them here. So what is happening here is this image and this image have almost the same noise level. And when we combine these two image, so this one we multiply with the inverse mask, this one we multiply with the mask, and then later on we combine them. And then we feed this noised but combined image back to the model, to this denoising step. So now when doing the denoising, the unit knows about the other region of the image. It just does not look at this cropped part, but it also looks at the entire image. And according to that, it starts denoise. And once we repeat this process across all inference steps, the result is a coherent in-painting image that respects the context. So the most important part here is synchronizing the noise level between the reference image and the predicted denoised image, and then merge them with the mask so that the model has context while denoising. Now let us go through the code and practical choice I made. So here I used a pre-trained diffusion model which goes by the name Google DDPM Celebrity HQ256. Because this model is trained on celebrity faces having 256 cross 256 resolution, you can load it using Unit 2D model from pre-trained, and this is how you gonna load it. Now we're going to try to sample from this model, the model that we just downloaded, that what kind of image it can generate. So this is going to be our simple denoising loop. I'm fixing the seed so that when you repeat the same experiment in your system, we get the same result. You can change this seed. So this seed affects the random number generation here. Here I am initializing a DDIM scheduler. This beta start and beta end are the same betas that have been used during the training of this diffusion model. So I have to use the same ones. You can find it if you go on Hugging Face to this repository, you can find this information there. Then I am setting the inference timestamp to 50 so that I don't have to wait until 1000 timestamp for a sample. Here I am generating random noise, which has the shape 1 cross 3 cross 256 cross 256, basically a batch of 1. And then I'm running my denoising. This is my denoising step, predicting the noise by passing into the model, and then using the scheduler.step method to remove the noise. And then the loop goes on. So let's see. So yeah, the images are pretty high quality. If you see 256 cross 256, let me change it to some another value, let's say 11. Yeah, you see it generates the picture of celebrities. Now we'll go to the in painting part because we don't need training for this in painting to be done. So I'm gonna load the image. This is the loading part. So this is my transformation, basically resizing the image to 256 cross 256, converting them to PyTorch tensor and bringing it to the range of 0 to 1, and then normalizing them so that the image lies in the range of -1 to 1. And in this code, I loaded the image. Basically, I cropped some regions so that the focus will be basically on the face and not anywhere else because the model is trained so. So I figured that it will work better in that way. Then I'm doing the transformation. And now we have the PyTorch tensor. I added a batch size and then pass it to the GPU. So this is how the image looks like. Now we'll go on creating a mask. So here you see, for now, ignore the Gaussian filter. I'll come to it. The first I created a mask using NumPy, which is a two-dimensional matrix with 256 cross 256 filled with ones. Then I set a box, basically this box, to have value 0. So this is the part where I want to inpaint like this. Then I convert the NumPy tensor to a PyTorch tensor. This will be my mask, which you see here, and this will be my inverse mask because we saw, right, we need both mask and inverse mask to do the in painting. And now if I plot it on top of the image, I see that this is the region that needs to be in painted. So how does the in painting go? This is the entire process of in painting. So some of the steps are exactly same as what we have done before. So which are those steps? So sampling a random tensor, doing the noise, passing it to the unit model to do the prediction, and then doing the denoising step. This part and this part are still the same as before. What has been added is these three lines. So what we are doing here, this is the part where we are taking the reference image, adding noise to it and getting the X noised. Then we multiply with this X noise the mask and with the XT version the inverse mask. Basically combine these two. Then we get the final combined XT value and then it goes through the denoising again. We repeat this process until the final denoised image is obtained. So now let's see the process. All right. So you see this, it does generate something pretty coherent. And what we can do is let's say if I invert the mask, now the head will stay the same, but the face will change. So let's run that. Now you see, now it tries to generate the face as coherent to the hair as possible. So you can, do your variations like that. And now what I did is I run the same loop, but for 10 times for different, random seed. So we get random images. So you see, they are pretty funny. Like they're trying to keep the head same while rather changing the face. And now if I do the inverse, yeah, now you see like some images are definitely going to be garbage, but some images look pretty coherent. Yeah, this one looks pretty coherent to me as well. But there is one problem. I don't know if you have noticed or not. There is a very sharp contrast between the generated part and the original part. How can we remove this? If you read the in-painting paper, they suggest to do multiple uh, noising and denoising step to take care of that. But I have a better solution. So what I did is instead of having such a crisp black and white separation, I smooth it. So I use the Gaussian filter and I smooth it using a sigma of 5. So this is how the smoothing looks like now. And now if I do the repaint using the same mask, you suddenly see you already start seeing that in the mask region, it's much smoother. Same happens here. The sharp contrast becomes lighter basically. At least I can see that there are some smoother region. You let me know in the comment section what do you think. One another take home message is that all the output look realistic enough, even though the base model probably never saw the Donald Trump's face, especially this new one. This method helps you generate new hairstyle, object swaps, background changes, and many more. In the next video, we'll do image to image diffusion. That is the base of many popular image editing demos where people transform a photo into a new style of composition. We'll show how image to image editing works at inference level and why it produces such convincing results. If you enjoyed this video, please like, share, and subscribe to Intelligent Machines. Share this with your friends or colleagues who like AI and image synthesis. If you have any questions or suggestions, put them in the comment below. Until next video, stay curious.